Hello everyone and welcome back to Express Academy. In this video we continue 101.2 module that is boot the system, which focuses on boot process of a Linux system. In the first part we learned about the boot process cycle and some key aspects like bootloaders and kernel process for booting your system. So buckle up and let's begin this course. First up is Initramfs. Initramfs or initial RAM file system is a compressed file system that kernel loads into memory early in the boot process. It provides a minimal environment for the kernel to initialize hardware, mount the root file system, and load the additional kernel modules. When you power on your computer, the Linux kernel initiates the boot sequence. However, before it can fully access the root file system, it needs to load the necessary drivers to the disk controllers, file systems, and other crucial components. This is where Initramfs comes to play. Initramfs contains essential binaries, libraries, kernel modules, and scripts. These components are selected to ensure that the kernel has the tools it needs to identify and mount the root file system, which might be on a complex storage device like a RAID array or an encrypted volume. Here's an example of how Initramfs is used in the boot process. First, the bootloader loads the kernel into the memory. In second step, the kernel initializes the hardware and mounts the Initramfs image. On third step, the Initramfs executes a small script that mounts the real root file system. On fourth, the Initramfs loads any additional kernel modules that are needed. On the last step, the Initramfs starts the init system, which is responsible for restarting the rest of the system. Initialization daemon process. Once the kernel loads, the first process that it will start is init. The init process in Linux is like the conductor of an orchestra. It kickstarts everything. Assigning the special number 1 for PID, it's the first program the Linux kernel runs during boot up, setting the stage for the rest of the show. Imagine you're starting a journey. Init is your guide, making sure everything is ready for the trip. It's like the gatekeeper between the deep down kernel world and the user-friendly space you interact with. As part of its job, Init deals with something called run levels. These are like different modes your system can be in. Maybe it's just you and the basis in the single user mode, or maybe it's a full-on party with a graphical interface in multi-user mode. Init decides which mode to go for based on your system's needs. Now, Init doesn't work alone. It has a bunch of scripts, kind of like a backstage crew, that it reads and follows. These scripts live in places like ets/init.d and tell Init how to set up the system. Think of them as instructions for getting everything in order, starting essential services, configuring network settings, and more. Traditionally, Linux used systemd init for this process, but think of systemd as the new kid in town. It's more modern and sophisticated init system with some extra bells and whistles. It brings things like correspond and smarter dependency tracking to the party and making the whole booting and shutting down process more efficient. Init is also a bit of a babysitter. Once it gets things going, it keeps an eye on services and processes. If something misbehaves and crashes, Init steps in, gives it a talking to, and maybe even restarts it to keep everything running smoothly. And when it's time to say goodbye, Init gracefully handles shutdowns and reboots. It sends signals to processes telling them to wrap things up neatly before the final curtain. Understanding Init is like having the backstage pass to your Linux system. It's an unsung hero, making sure everything starts up, runs, and closes down just the way it should be. So whether you're a curious beginner or seasoned user, knowing a bit about Init gives you a backstage view into how your Linux system takes its first steps into the digital world. The configuration file that controls the behavior of the init daemon is the ets/inittab file. If the bootloader configuration does not specify a run level, then the init default is used. This setting defines the default run level that system should enter. This is typically 3 for text-only server and 5 for GUI environment. Run levels are covered in more details in 101.3 module. If you are using a later Linux distribution, then run levels are replaced with targets but hold the same purpose. If you run which init in your terminal, you can see your system init. And if you want more information about your init system, run this command: readlink-f/sbin/init. If you type in ps-p1, this command shows you the first process ID, which is your init system. There are different init systems: SysVinit, systemd, and Upstart. SysVinit is based on Unix systemd. Not being used much, but people loved it, and you may see it on older machines or even on recently installed ones. Systemd is the new replacement. Some people hate it, but is being used by all the major distros. It can start services in parallel and do a lot of fancy stuff. Upstart was an event-based replacement for the traditional init daemon. The project was started in 2014 by the company behind Ubuntu to replace SysV, but did not continue after 2015, and Ubuntu is now using systemd as its init system. Now let's check out the init systems, and we are starting with SysVinit. SysVinit refers to the systemd init system, which is an older and traditional init system used in many Unix-like operating systems, including Linux. Init systems are responsible for initializing the user space during the boot process and managing system processes. SysVinit follows the principles of systemd Unix and is characterized by its use of run levels to define different states of system operation. Run levels represent various modes in which the system can operate, such as single-user mode or multi-user mode with a graphical interface. The heart of SysVinit lies in initialization scripts, often residing in directories like ets/init.d or ets/rc.d. These scripts, executed during the shift between run levels, take charge of configuring different aspects of the system. Unlike more modern init systems, SysVinit adopts a sequential startup approach. Services are started or stopped one after another, adhering to their specified order in the run level scripts. Service management typically involves the use of tools like the service command or ets/init.d scripts. They empower administrators to start, stop, restart, or check the status of services. Configuration files play a pivotal role in SysVinit. Locations like ets/inittab or the ets/init.d directory house these files, defining the behavior of the system and outlining which services should be initialized or halted in each run level. At the core of the SysVinit is the init process marked with PID1. As the parent of all the other processes, it takes center stage in the boot process. Tasked with transitioning between run levels, it executes the necessary scripts to shape the system's configuration. While SysVinit has been a long-standing and pivotal init system, it's essential to acknowledge that modern Linux distributions are transitioning to newer systems like systemd. Nevertheless, comprehending SysVinit remains valuable for historical context, and compatibility with systems is still utilizing this traditional init system. Systemd. Systemd is a comprehensive system and service manager designed to handle the initialization process and manage various aspects of system and service control in Linux operating systems. It serves as a replacement for traditional init system like systemv init or SysVinit and offers a more modern approach to system initialization. One of the key features of systemd is its ability to parallelize the boot process, which means that it can start multiple services simultaneously, leading to faster boot times. This is the departure from the sequence nature of older init systems. Systemd also excels in dependency tracking, automatically determining the order in which services should start based on their dependency. This streamlined approach enhances system efficiency. The configuration of systemd is centralized and organized in files under the ets/systemd directory. These files include configurations of services, targets, or run levels, and other system settings. This centralized approach simplifies system management and configuration. For managing services and system states, systemd introduced the systemctl command. This command allows administrators to start, stop, restart, enable, or disable services easily. It provides a unified interface for interacting with various aspects of the system. In terms of logging, systemd incorporates a journal system that stores logs in binary format. This format facilitates efficient searching and analysis of the system log. The journalctl command is used for query and view of the logs managed by systemd journal system. Systemd integrates with control groups or cgroups, a Linux kernel feature for managing and isolating resource usage of processes. This integration enables systemd to have better control and monitoring capability over system resources. Another noteworthy feature is socket activation, where systemd allows services to be started on demand when a connection is made to a specific socket. This feature enhances resource efficiency by starting services only when needed. Systemd is made around units. A unit can be a service, group of services, or an action. Units do have a name, a type, and a configuration file. There are 12 unit types: auto mount, device, mount, pause, scope, service, slice, snapshot, socket, swap, target, and timer. We use systemctl to work with these units and journalctl to see the logs. While systemd has received praises for its modern design and feature, it has also been a topic of debate on Linux community. Some appreciate the advancements it brings, while others express concern about its departure from the Unix philosophy of doing one thing well. Regardless, systemd has become the default init system for many major Linux distributions, influencing the landscape of Linux system management. Now let's see some of the systemd commands. Let's start with systemctl. The first one is systemctl list unit, which displays a list of active units. You can see devices here like sound card control unit or your system backlight. Or you can specify a specific type for list unit command. Here I specify targets as type. Systemctl get default will display the default target that systemd will use when system boots. Mine is graphical target. Now let's check out journalctl. Journalctl --no pager command in systemd is used to view the systemd journal logs without using a pager. Journalctl-xe is used to view systemd journal logs with a focus on showing the most recent entries along with additional details for troubleshooting. Here you can see this unit has entered in dead state. Again, you can use --help option to see all the possible options for this command. We have --user that displays the current user journal, or --since, which displays entries not older than a specified date. Dmesg. The dmesg command in Linux is a tool that lets you access and view messages generated by the kernel. When your computer boots up and runs, the kernel produces various messages about the system's hardware, device initialization, and other events. The name dmesg stands for Display Messages. Dmesg allows you to view and control the kernel ring buffer. The kernel ring buffer is a special area of memory that stores messages generated by the kernel and its device drivers. These messages can provide valuable information about the system's hardware, software, and overall health. When you run the dmesg command in the terminal, it shows you these kernel messages. It provides a snapshot of recent events, making it useful for troubleshooting and understanding what's happening under the hood of your Linux system. For instance, if you connect the USB device, the kernel might produce a message in the dmesg output indicating the detection of a new hardware. Similarly, if there are errors or warnings related to the hardware or device drivers, they will be displayed. Typically, you would use the dmesg command without any options, and the output might be extensive. To make it more manageable, you can use tools like less to scroll through the messages. For example, you could use dmesg pipe less to view messages one page at a time. The dmesg command is valuable for troubleshooting scenarios, helping you identify hardware issues, understand device initialization process, and get insights into kernel-level events. It's a handy tool for administrators and users looking to gather information about the system's behavior and diagnose potential problems. Now let's check out some of dmesg-related commands. First, let's see dmesg with no option, which prints all the messages buffer of the kernel. Dmesg pipeline grep USB displays only USB related messages. For human readable display, use dmesg --human. Sudo dmesg -c will clear ring buffer, and dmesg -n will only displays critical messages. var log messages. In Linux, the var log messages file is like a diary for your system. It's a place where the operating system and various programs jot down important information, events, and even issues that occur during the normal course of running. Located in the /var/log directory, this file acts as a central repository for a wide range of system messages. These messages cover everything from kernel-related events and hardware details to notifications from different services and applications running on the system. When you open the val-log messages file, you'll find a chronological record of what has been happening on your system. When you open the val-log messages file, you'll find a chronological record of what's been happening on your system. Each entry comes with timestamp so you can see when an event occurred. This chronological order makes it a valuable resource for administrators and users trying to piece together the sequence of events leading up to a particular situation. The messages are often categorized based on their severity using labels like info, warning, error, and others. This makes it easier to spot critical issues and just keep an eye on regular system activities. Administrators frequently turn to this file when troubleshooting. If something isn't working quite right, or an application is misbehaving, checking val-log messages can provide valuable clues and context. It's a bit like flipping through pages of a diary to understand what happened on a specific day. To manage the size of log files and prevent them from taking up too much space, log rotations might be in play. This involves archiving older entries and creating a fresh log file. It's like starting a new chapter in the diary while preserving the old records. Keep in mind that the structure and content of val-log messages can vary between different Linux distributions. Some systems might use different log files or organize information in alternative ways within the val-log directory. In security-focused scenarios, administrators often review log files, including val-log messages, to identify any signs of unusual or suspicious activities. This proactive approach helps detect potential security breaches or other threats to the system. So think of val-log messages as a living document, a record of your system's journey, its ups, downs, and everything in between. It's a powerful tool for understanding and maintaining a healthy and secure Linux environment. And that's it for this video and module. It was a bit long one, so make sure to watch it twice. Hope you enjoy it, and if you do, make sure to subscribe and recommend this channel to your friends.